Hello chemists, so in today's lesson we are going to be looking at electrophilic addition. This tends to be a reaction reserved for alkenes or whenever you see CC double bonds. So let's get started looking at the mechanisms of electrophilic addition. So we're going to begin today looking at alkenes and changing them into halogenoalkanes, in this case a dibromoalkane. This is an example of a halogenation reaction. That's not the name of the mechanism. All of the mechanisms I'm showing you today are electrophilic addition. Let's have a look at an overall reaction scheme for this reaction. Here I've shown propene and bromine, Br2, so that's a halogen. And the bromine is going to add across the double bond. We can see there was the original position of the double bond. And we can see we've added a bromine atom here, which was this carbon here, and here, which is this carbon here. So the name of this product is 1,2-dibromopropane. Now this follows an electrophilic addition reaction in terms of its mechanism, and the reagents in our case are liquid bromine at room temperature. The bromine's a liquid simply because that's its standard state at the given temperature. Now this will follow two potential mechanisms, but I'm going to talk first about the more likely mechanism. Take the propene and the bromine. A molecule of bromine is non-polar because each atom has exactly the same electronegativity because they're the same atom. But that's not to say that a temporary dipole could occur inside the molecule due to a sudden shift in electron density. So we could label a delta positive and delta negative on the bromine based on the idea that a temporary dipole must exist at a given moment in time. But obviously that would keep switching sides. Now, the alkene itself, the CC double bond, is an area of high electron density, so it's going to be attracted towards this delta positive bromine, and it's going to attack the bromine atom. Bromine can only form one bond, so if it's going to make a bond with one of these carbon atoms, it needs to break the bond with its other bromine atom. So we're going to show the breaking of that bond there. That's called heterolytic fission. Next up, we're going to show our intermediate. Now, it's best if you imagine double bonds like a hinge. This arrow coming down here basically shows this lower bond turning and then going down here. So it's like hinging downwards to go down. You can see it's now here. So imagine that this bond was that double bond, the lower one of that double bond. I've put the bromine here, and we can see now what we've got is a positively charged carbon atom, because in this bond, one of the electrons in this, let's have a look at this, just this lower one of the pair. One of the electrons belong to this carbon, one of them belong to this carbon. So if you take the whole pair and move them down to this position here, then this carbon is going to be deficient in one electron as one of the pair was originally its. So now we can see what we've formed is what's called a carbocation, a positively charged carbon atom. So when we broke this bond originally in the molecule of bromine, we would have created a bromide ion. So I'm going to show that here as Br-, and I'm going to show its lone pair of electrons on it here. That's now going to attack the carbocation like this. There we go, we've attacked the carbocation, showing the formation of a bond. And here we go, there's our product, as described earlier, 1,2-dibromopropane. Now you might be wondering why this is the more likely mechanism. Well, if we look at the carbocation that's generated, this carbon is bonded to two other carbons, which means that this is what we call a secondary carbocation. Now, hold that thought for a moment when we look at the other mechanism, the less likely mechanism. Again, we can label a delta positive and delta negative slight charges due to a temporary dipole on the bromine molecule. The double bond is going to open up and attack one of the bromine atoms. The delta positive one will always be attacked, and the bromine-bromine bond will break. Last time I asked you to imagine that this bond was hinging down and going down here. Now imagine that this bond is hinging round like this and coming down out of here. Well, if we do it like this, then we'll generate the carbocation on this first position here. And you can see that this carbocation is only bonded to one other carbon atom. So this one's a primary carbocation, whereas through our previous mechanism, we'd shown a secondary carbocation. The bromide ion generated will again attack the carbocation, forming a bond with it, and we can see that the same product has been made, 1,2-dibromopropane. Now, why is this the less likely mechanism? Well, we can describe this due to something called the inductive effect, or the positive inductive effect, to be specific. Our secondary carbocation versus our primary carbocation. We can say that our secondary carbocation intermediate, it's called an intermediate because it's not quite yet the product, is more stable than the primary carbocation intermediate. Why? Because it's got the positive inductive effect of two neighbouring alkyl groups. An alkyl group is just a carbon group. Notice how the secondary carbocation has two carbon groups, two alkyl groups. And essentially what's able to happen is the electrons in this bond here and the electrons in this bond here are able to be drawn towards that positively charged carbon atom, the carbocation, stabilising its positive charge, which means that it can exist for a longer period of time and therefore it's more likely to react because it's more likely to be there in the first place. If we look at our primary carbocation, we can see that it's only got the positive inductive effect of one neighbouring alkyl group because it's bonded to only one carbon. So therefore it's not going to be as stable and intermediate, therefore it's less likely to exist for a prolonged period of time, so therefore a mechanism is less likely to use it. This wording here is the exact wording you need to use in your exam in order to justify why this mechanism through the secondary carbocation intermediate is the more likely mechanism. Now, although both of these give the same products and both mechanisms lead to that, you should always draw the mechanism that goes through the more stable carbocation intermediate. That is the accepted mechanism to go for. In this next section, we're going to look at a slight variation on the reaction you saw previously, as these products have the potential to yield position isomers, which is a type of structural isomerism. We're going to be converting an alkene into a halogenoalkane. So again, we're looking at halogenation. This time we're going to react our alkene, or unsaturated compound with a CC double bond, with a hydrogen halide. So that could be hydrogen chloride, hydrogen bromide, hydrogen iodide, etc. Now, we get two different products here, a major product and a minor product. And this is because the hydrogen halide, if you imagine it beneath this here, in the same orientation it is at the moment, well, the hydrogen is added here and the bromine is added here, yielding this major product, 2-bromopropane. Now imagine this molecule flipping it almost like a horizontal flip, so the hydrogen's this side and the bromine's this side. Well, in that case, the bromine would add here and the hydrogen would add here, in which case you'd get this minor product. The mechanism for this reaction, again, is electrophilic addition. And the conditions you need are a hydrogen halide, call that HX, but again, it could be hydrogen chloride, hydrogen bromide, hydrogen iodide at room temperature. And we have two different mechanisms. Let's have a look at the mechanism for our major product, getting the bromine on carbon number 2 here. So, we've got our alkene and we've got our hydrogen halide. Hydrogen halides are different to halogens in the fact that they do have a permanent dipole. Bromine is more electronegative than hydrogen, so bromine becomes slightly negative, labelled as delta negative, and hydrogen becomes slightly positive, labelled as delta positive. Let's do that. There we go. High electron density in the alkene enables it to act as a nucleophile towards our electrophile, the hydrogen atom here. So there we are. We've got our electrophile being attacked by our nucleophile, so nucleophile, electrophile, and hydrogen can only form one bond. So for this reason, it's going to need to break its bond with bromine to form a bromide ion. Imagine this bond now hinging downwards like this. So we're going to have the hydrogen attached on this carbon here. Because we've taken away one electron from this carbon here, it's going to form a carbocation. This carbocation is secondary for reference. And the bromide ion that we generated earlier is now going to act as a nucleophile attacking the carbocation. This will form our 2-bromopropane product. There it is. Okay. Now let's have a look at the mechanism for the minor product. This time, what we need to imagine is that the double bond hinges down this way. So it will first bond on this carbon here. So the mechanism's the same as before, but we need to imagine that it's hinging in a different way. Break the hydrogen-bromine bond, but this would yield this intermediate. If we hinged this bond down this way instead of hinging it down that way, then we'll end up with this intermediate. Now this results in a primary carbocation, which hopefully you remember from the last one is less stable because the positive inductive effect is not as strong. It'll be attacked by our nucleophile, which is bromide, and this will form our 1-bromopropane. So now let's justify why this is the major product and this is the minor product. Again, we're looking at a comparison between a secondary and primary carbocation. And we can argue that our secondary carbocation intermediate is more stable than the primary carbocation intermediate due to the positive inductive effect of two neighbouring alkyl groups. So if our reaction is more likely to follow this mechanism, then we are more likely to get this product. So therefore we can call this our major product. And remember that these are position isomers of each other, a type of structural isomer. And remember the definition of structural isomer is same molecular formula, different structural formula. And when you say that it's got structural isomerism, you always need to define a type of structural isomerism. Is it chain, position, or functional group? In this case, we're looking at position structural isomerism because the bromine has changed positions. Next, let's look at how we can convert an alkene into an alcohol via hydration. I've drawn a reaction scheme here. We've got an alkene, ethene, and water. And we're going to convert this into ethanol. You can see that this carbon here has had a hydrogen atom added to it, and this carbon here has had an oxygen and a hydrogen atom added to it. The mechanism that this follows is electrophilic addition, and the reagents and conditions are as follows. You need a solid phosphoric 5 acid catalyst, so that's its oxidation state of phosphorus in phosphoric acid, okay, which has the formula H3PO4. You need to react it with water in the form of steam, and the conditions for this are highly specific. They are 300 degrees Celsius and 60 atmospheres of pressure. Let's have a look now at our mechanism for how this reaction functions. The solid phosphoric acid catalyst is a source of H+ ions, hydrogen ions. And the hydrogen ion here is our electrophile that's going to be added to the double bond. So the bond is going to hinge open and attack our hydrogen ion. This will result in a carbocation intermediate, as we've shown before. Because this molecule that we've drawn at the moment has symmetry, it really doesn't matter on which carbon atom you draw the carbocation. But obviously if this was a longer chain, then you would need to consider exactly which carbon to turn into the carbocation so you can choose the more stable arrangement. Our water, that's in the form of steam, is now going to attack that carbocation because the water is going to act as a nucleophile here. Let's show that. From the lone pair onto a carbon atom. When you're drawing these, make sure your curly arrows move straight from the centre of the lone pair to the atom. Don't attack the positive charge and don't move randomly from the atom or from the negative symbol or sign. Move from a lone pair to an atom or from the middle of a bond to an atom. This will create an intermediate that's got a charge because we haven't actually removed one of these hydrogens yet to form the OH group, the hydroxyl group of the alcohol. So therefore, oxygen is going to be positively charged because one of these bonds is technically a dative covalent bond. So what we need is to show the loss of one of these hydrogens. And that's very straightforward. All we do is an arrow from the oxygen-hydrogen bond onto the oxygen. Therefore, that hydrogen will give the pair of electrons to the oxygen, neutralising the positive charge. This will result in our product, and the H+ ion will be regenerated. And this is important because H+ was there at the start, and it's also there at the end. It shows the role of H+, remember all acids are a source of H+. It shows the role of H+ as our catalyst, which means that our acid must have been our catalyst because H+ has been regenerated. Next, we're going to look at a variation on the hydration mechanism, specific for when sulfuric acid is used as a catalyst instead. Take propene, again, and react it with water. then we're still going to result with an alcohol as a product, except because propene is longer than the previous example that I showed you, ethene, we can now have the potential for major and minor products. Now that's perfectly possible with the previous mechanism I showed you. However, the mechanism that uses sulfuric acid is a little bit more common in the lab, whereas the phosphoric acid method is a bit more of an industrial process for the hydration of ethene specifically. So sulfuric acid tends to be used as the catalyst for alkenes longer than ethene. So again, this is following the electrophilic addition mechanism, and our conditions are as follows. We're going to use a concentrated sulfuric acid catalyst, and we need to heat it up with water. Let's have a look at the mechanism for this major product here, this propan-2-ol. So if we take propene here, this time, rather than showing just H+ from the acid catalyst, if you use sulfuric acid, you need to show the whole displayed formula for sulfuric acid, which I've drawn like this. And I've shown the bond between this O and H because they're going to be involved in the mechanism in a moment's time. We could say that this hydrogen is delta positive and this oxygen is delta negative because oxygen is more electronegative. This is also going to be true in different positions on the molecule, but we're not really interested in other positions because they're not directly involved in the mechanism. The alkene is going to attack this delta positive hydrogen, and the bond between the hydrogen and the oxygen are going to break. Hopefully you're spotting a trend here. Again, we can imagine this opening up like a hinge. Will it go this way or will it go this way? Well, if it hinges down towards the left, then it will generate a carbocation here, which is secondary. If it hinges down towards the right, it would generate a carbocation here, which would be primary. And given that this is the major product, we need to go for that secondary carbocation intermediate, which I've shown here. So we've now generated our secondary carbocation intermediate, and we've got the hydrogen sulfate ion, that's HSO4-, left over. This was formed as a byproduct of this bond cleavage here. Well, this oxygen is now able to act as a nucleophile, attacking the carbocation as such. And this will leave almost the hydrogen sulfate ion kind of hanging off of the rest of the molecule like this. Now, to actually show the conversion of this hydrogen sulfate intermediate to our major product mechanistically is quite challenging. So at A level, once you get to this stage here, you don't need to mechanise any further. All you need to do is show the addition of water, and therefore you get your product and it regenerates the sulfuric acid catalyst. Let's now have a look at the formation of our minor product. Right then. So hopefully now what you're thinking is, well, to get to that minor product, which was a propan-1-ol, then all we would need to do is generate a less stable carbocation intermediate. So when we attack the delta positive hydrogen from the CC double bond, what we're going to need to do is generate a less stable carbocation intermediate, that being our primary carbocation. So this hydrogen, this has got a hinge down this way, and the hydrogen's got a bond on here. So let's break that bond there and move on to the intermediate. This is hinged down this way, so the hydrogen's going to be on this second carbon here. I've just shown this CH3 bit rotating round a little bit and I've displayed it. Hydrogen sulfate ion is going to attack the primary carbocation this time to form this hydrogen sulfate intermediate. And when you get to this step, show water hydrolyzing that bond and the reformation of the sulfuric acid catalyst. Okay, so there we go. You can see that this mechanism looks a little bit more complicated than it really is. Essentially, the mechanism is the same as it was previously for any other electrophilic addition reaction. The only complications are that you need to remember the structure of sulfuric acid and you need to remember to break the bond in this less elaborate way at the end here. Now let's justify this major product as we've done before. We've got two carbocation intermediates potentially. We've got a secondary carbocation, which is more stable than the primary carbocation intermediate due to the positive inductive effect of two neighbouring alkyl groups. Now if we look forward towards our products as well, we've got propan-2-ol versus propan-1-ol. And these are position isomers of each other, which is a form of structural isomerism. And remember that your definition for structural isomerism is compounds with the same molecular formula but different structural formulae. I want to finish off now with some top tips that I've got for electrophilic addition reactions. The first tip is, if you're ever asked to outline a mechanism, always go for the mechanism which involves the more stable carbocation intermediate where applicable. Remember that the most stable carbocation that you could go for would be a tertiary carbocation, where the carbon is bonded to 3 others. Secondary is then second most stable, where the carbon is bonded to 2 others. And primary carbocations are the least stable, where that carbon is bonded to only 1 other. Remember that if you've got an alkene, propene or longer, then you can get position isomers, which are a type of structural isomer. So you need to use the right mechanism to get that particular position isomer that you're after. And sometimes the exam questions ask you for multiple products. Remember, those products with electrophilic addition are likely to be position isomers of each other. Remember that position isomers are not going to occur if you just add a halogen, because actually you're adding a bromine in this case to each carbon either side of the double bond. So it doesn't matter which one you add to each carbon because they're both the same thing. But you still need to follow the more stable mechanism. And don't forget to add partial charges onto your electrophile, Br2, HBr, onto the sulfuric acid catalyst. Well then, I hope you found that video on electrophilic addition useful. Make sure you come back for the next video where we're going to be looking at elimination mechanisms. Thanks very much.